I'm going to tell you about the actual science behind how a rocket mass heater works, while I show you how I did the metal work for my mini version, which is made entirely out of scrap junk. Right now is the most difficult point of any project. I'm not sure what I should do first, but I know what I can do first, and that's chop the stuff off of this pancake compressor and start turning it into the burn chamber. This thing is a little too thick for my plan, so I'm gonna see if I can squish it. Big hammer. Work smarter, not harder, right? Bag of gravel makes all the difference. I need to find the center of this thing. Should get me close enough. Guys have those little tools they use to find the center of something for turning on a lathe. This is basically the same thing. The sides just don't come down far enough to touch the container, so I just have to eyeball it. Clamps helped. Looks good enough for me. Cutting circles with the angle grinder is no fun. I didn't have any big steel pipe laying around, but luckily a friend of mine did, because he just got a truck that had 5-inch exhaust on it, and he didn't want 5-inch exhaust on it, so he gave me these for free. Lappy-doo. You can see the line where there's no more chrome. Come on, fit. Please. Yeah. Uh-oh. Too far. Come on. Too far that way now. Oh, almost. Stay on target. Stay on. Oh. Is that it? Yep. There she is. Time for the chimney pipes. Right there. I am gonna quit for tonight. It's after 2 in the morning. I'm gonna light some paper on fire and test it. Yeah! I was hoping smoke would come out the top. I mean, it does work. You just can't see it. Oh, you can see the smoke now. Well, I can. I don't know if it's showing up on camera, but whew, I want to keep working. But I can't! Stuff to do tomorrow. I was gonna leave this at what it is now. Since it's steel, it's not gonna last because the temperatures that you reach inside of a rocket mass heater thing get too hot. A lot of people are reporting temperatures between 1500 and 2400 degrees inside of their burn chambers. Even though the melting point of steel is 2500 degrees, it still corrodes and deteriorates the steel very quickly when you get up into really high temperatures. It does this thing called spalling, which is rapid oxidation, where it's almost like delamination oxidation. It'll probably still last for at least this winter and probably next winter too, but then I'll have to rebuild it. And the point of this project was to do everything as cheap as I could with what I had laying around, but I realized that I have a really good solution to keep this shape and make it last basically forever. The problem is I need to go buy another thing. Now it's time to build a second part. out of this. There's a metal company that used to be near me, and they let me pick through the scrap bin and take whatever I wanted because they said it would cost more to write up an invoice than it would the amount of money that I'd have to pay for the steel that I took. So they let me take a bunch of stuff. It was awesome. I wasn't sure what I was going to do with this, but I knew that I'd use it to make something eventually. It's going to come in real handy. It's about to get turned into the cage for my mass exchanger portion. Here we go. Made some extra marks earlier. No way I can put this thing together inside of here because I can't reach it. Cut it into chunks, weld it back together. That way I can reach as I build it inside the cage while it's in place. I'm going to address comments from the last video real quick. A lot of people reference other types of stoves and heaters that have been around for a long time that they knew about. All of those stoves are incredibly expensive to build, or they have limiting factors that I couldn't use in my garage. I'm very specifically building this heater the exact way that I'm building it because it's incredibly cheap for me. It's only going to cost me about $140 for everything that I had to buy to do this because I sourced so many things from scrap. A lot of the heaters that I looked up, if you were to build one according to the way that they did back when, or even just buy one of these modern units, most of them will range you somewhere in the thousands of dollars. Far cry from 140 bucks. Also, in case you don't see enough differences between what I'm building and what's in those stoves in this video, in the next video I'm going to talk about all of the little changes that I'm making to make mine even more efficient than any current design that I've seen. Second issue from the comments. In the last video, I said that electric heaters are incredibly inefficient. They are. Electric heaters are 100% efficient. Theoretically, all of the energy that you use is converted into heat. Problem is, they're terribly inefficient because the power that you draw is created, I wrote this down, of the electricity generated in the United States. 64.5% is from burning stuff. 20% is from nuclear, and the rest is from wind, geothermal, hydroelectric. But 64.5% is the vast majority. And even at power plants that burn stuff that have the peak of technology and the most efficient conversion from heat energy from burning stuff into electricity only reach about 48% efficiency. 48%. So if you convert the chemical energy that's available in whatever you're burning directly into electricity, that would give you 100%. They can only hit 48%. Now, I'm absolutely positive that somebody out there that's an engineer can actually do the math on this and figure out how much energy I'll be extracting if my intake temperature is, say, 30 degrees Fahrenheit and my exit temperature is 120 degrees Fahrenheit, which is what a lot of these people experience that build these heaters. You'll be able to figure out what percentage of the heat is remaining in this room and therefore know the percentage of efficiency that I'm getting from burning stuff. The reason it's frowned upon to burn wood yourself is because most people don't burn wood at a temperature that destroys all of the volatiles that come out of the wood when it's being pyrolyzed and burned. But mine will, so I'm not polluting and it's efficient. And on top of that, energy is lost in the conduction of that electricity to your home. Now that's going to vary widely on how far you are from a power plant, where it's coming from. And remember, 48% was from the most efficient. Most power plants that burn stuff are only around 30% efficient. I think that's what it was. I didn't write that down. So I hope that clearly explains why using electricity to heat your home is incredibly inefficient, at least if you live in the US. This bottom piece still needs chopped up a little bit though. Time to use some exhaust pipe. This part that I'm about to weld together right now is going to be the bottommost pipe section of the heat exchange portion of the mass at the bottom of the cage, and it's going to serve two purposes. After these are put together, I'll be able to take some measurements and remove a section of this for an access door to use for cleaning out and for priming the system, which means it's a perfect time to talk about the thermodynamics of what's going on inside of a rocket mass heater system. Don't worry, that's just a big word. The concept is not that complicated. I almost forgot. I have a demonstration that I prepared to illustrate the concepts. That way it makes this really easy to understand. I have a candle right here. I put this tube out in the snow. When I hold it up to the candle, it blows the flame because the air that's inside becomes more dense as it cools, and then it rushes out the bottom of the tube and it blows the candle's flame. I know that's not that interesting, but this is the part that's cool. I'm just gonna warm up the bottom of the pipe. Woo! Yeah, the bottom of the pipe is very hot, but the air is still traveling that direction. And this illustrates an important concept. The bottom of the pipe is hot and it's creating hot air, and hot air rises, but it's not able to push against the denser cold air that's at the top. Even though it's lighter and it wants to go up, you have enough weight from the dense cold air that it still pushes it that direction. This is very important for what we're going to talk about. Yeah, it's still real hot and it still is going that way. Now the whole bottom half is hot and the top half is still cold, and now you can see that it's drawing the flame from the candle into it instead of blowing it away from it. Even though the top is ice cold. Now you see the reversal, and my demonstration is complete. You need enough low density air to overcome high density air inside of the system. Priming a rocket mass heater means that you are creating airflow in the direction that you want it to go. You don't want to start a fire in your burn chamber and have the exhaust go out of the intake. The reason I'm using this as the priming chamber is because it gives the warm air that is low density a nice easy path to go up and out. Priming typically isn't necessary, but I need a clean out port anyway, so this will work for that as well. And I hate it when people say heat rises, because heat doesn't rise. Heat is just energy. It goes in all directions. Hot air rises because it has lower density and thus less mass per volume, giving it less weight. Part of the reason why the hippies that do a lot of the videos that I found that have information on these irritated me so much. Words have definitions so that you can communicate and someone can understand the concept behind what you're saying. Let me just define a couple things real quick so that we're on the same page. Weight is the combination of mass and gravity. Mass is the total heft of the matter that makes up something. Basically, it defines something's momentum regardless of gravity. This small piece of metal has weight. If you're outside of the Earth's gravity, it does not have weight, but it still has mass. Heat is a word that we use to define something's perceivable energy level, and you get expansion when something is hot. A perfect illustration of this concept is a thermocline in a lake. During the summer, there's hot water on top, and then the bottom is cold water. Water is very interesting because it is densest at 4 degrees Celsius, I believe, 40 something Fahrenheit. Now it's special because when it goes above that temperature or energy level, it becomes less dense. But as it goes colder than that, it also becomes less dense. As far as I know, it's the only thing that does that. If you've ever jumped in a lake in the wintertime, you know that the water at the top is very cold and the water underneath is actually warmer. And that reverses in the summer because it passes that 40-degree mark and the warm water becomes less dense and it moves to the top and the cold water moves to the bottom. That area in between the heat separation is called the thermocline. Go in your home. Okay. The point that I'm trying to make is that heat doesn't rise. Something with less density will rise above something with higher density, which is very important for understanding how these rocket mass heaters work. And also why it made me irritated, to say the least, when I watched a bunch of videos of these hippies making rocket mass heaters and not explaining the science behind it, but just, I'm honestly not even really sure if they know what's going on. They say that they're teaching you how to do it and all this. They don't give you any real information. They just tell you, oh, well, I know this from my experience, so this is the way that you have to do it. Well, that's great that you got one to work well, but why don't you explain the principles and the science behind why it works to people instead of just going out and trying to sell a bunch of books and DVDs? And I would venture to guess that that stuff probably doesn't even have any real information in it either. When you try to educate people about how to come up with it with the stuff that they have available to them. There's one video in particular that really irritated me, and I think I'm gonna do a Patreon special video for it because it made me mad, but it was pretty funny at the same time because of the lack of understanding that the expert had on what he was talking about. So if you're one of my patrons, look forward to that. Everybody thinks you have to follow these stupid rules that have been put out by these experts on rocket mass heaters, and I think a big part of that is because they don't understand the science behind it. And that's a big reason why I wanted to do the video on this. But I do feel bad. There are some people out there who know what they're talking about. There's this guy, Rob Avis, that used to be an engineer. He's got some videos and he understands the system behind it. His videos are much better than pretty much every single other video that I've seen that's out there. The company he started is called Verge Permaculture, if you want to look that up. The reason I got turned on to rocket mass heaters is because I know a guy and he contacted me. I talked to him in like 8 years and he was like, oh, hey, this guy's coming to teach me how to make a rocket mass heater. I'm getting one put in my house. Why don't you come hang out for a couple days and you can see how to do it? Oh, that sounds cool. 2 days before the event, he told me to make sure that I buy my ticket. That was $500 or something insane like that. It was at least $350. I didn't do it. Basically, you get a bunch of people to commit and then try to make them feel bad because they committed to it and they're not willing to spend the money to come learn the wise lessons that some hippie that's trying to get rich off of this is doing. I mean, how are you going to call yourself an environmentalist, not teaching people the science behind the thing and just forcing them to buy your plans so that they can follow exactly what you did? Hypocrites. But I couldn't find any information on ratios between tube and pipe diameters, If your burn chamber has this volume, then your whatever should have this volume. And all they talk about is, oh, the fire burns sideways inside the burn chamber. To get an efficient burn, you need high enough temperature and enough available oxygen so that you oxidize everything that's there. It's got to be hot. Well, does she want to come on? Oh, there it goes. The problem is you need the heat in the right place, as you saw when I did that candle test earlier. So here's the deal with getting enough air in and keeping your temperature hot. Very insulated burn chamber, that way the heat stays inside it. You want that to be insulated. This is the mass heat exchange portion. This should not be insulated so that you can draw all of the heat out of the exhaust. And for that, you need the correct flow. And that's why I did that candle thing earlier. Even though I got it really hot right there at the bottom, the air was still flowing the wrong direction through it, just like it would be with this. So your intake, you want to keep close to the ground. Your exhaust, you keep it high. That way the low density air tries to go up and thus draws fresh air into your intake, and then it's heated and you extract the heat. You get it. Thing is, all they keep talking about is making this part really hot so that you get that flow, which if it goes up and it dumps its energy and starts coming back down, that hot exhaust gas is higher density than the air that's inside of your burn chamber in the heat riser. So yes, it would want to fall compared to that. But just like in the candle thing, it didn't matter that I had a very hot section of the tube, the air still came down. If you do start a fire in your burn chamber and it's really hot and it lowers the density of that air considerably, you could potentially have enough force coming through your exhaust that would push it the wrong direction. I got really tired of people asking how big their feed, burn chamber, and exhaust or chimney tube should be so that they get it to work. It's simple. Get enough low density air trying to go up that it, and momentum plays a part in it too. You want the air to go that way. It's not that hard to figure out. Get it warm, it'll go out your exhaust. But they don't talk about that, so that's why these people are asking these questions. Once the intake air comes into the burn chamber has an extra 4.5 extra square inches. So when the air comes in fast, it slows down. Once it slows down, it gives it an opportunity to sit in here with the fuel and allow more reaction to take place, thus giving you a more efficient burn. In most of these heaters, people have square burn chambers and square... This part's all square. Mine's more round. A circle is more insulating than a square. You have more surface area on a square per volume than a circle. So this whole section should be round, not square. And my heat exchanger pipes are going to be square, and these guys are always telling people to use round pipes, which means they're teaching people to use less insulation on the hot side, where you should have it, and more insulation on the heat exchanging side, where you should have less of it, because you want to pull the heat out at that point. That's why I think this is going to be very efficient. This section of tube will allow me to guaranteed prime my system, because the hot air that's supposed to come in from the intake side will come in very low in the bottom half of the tube, and the exhaust from this will come off the very top. So if I start a fire in here, obviously the warm air will stay at the top and it'll try to flow up here before it tries to flow up there, and it would draw air through the system the direction it's supposed to go. On the forums and everything, it seemed like a lot of people were confused about this. Nobody was giving good explanations. They were just talking about following the 1-2-4 principle. 1 foot intake, 2 foot burn chamber, 4 foot heat riser, which ends up taking a huge amount of space. Mine is 1 foot intake, 3 foot burn chamber, 2 foot heat riser, but my burn chamber kind of doubles as a heat riser because it curls around and goes vertical. So that means I have a 1 foot intake and a 3 foot burn chamber and a 5 foot heat riser, but it's only about this big. If you're wondering why I'm welding all these pieces together, it's because I split it so that I can weld and seal everything from the inside. And then when I weld this on, I can weld and seal that stuff from the outside. There's no way I'd be able to weld the whole way down in that crevice to be able to get that sealed tight. This section is almost complete, but I am running out of time very rapidly to try to get this video out. But as I was finishing welding up this section, I realized that the pipe that I have is too small to give me a good chimney sleeve form thing. And then I found this, which is left over from the fire tornado gun. It was a little big, so I cut a section out and welded it together. So I took the extra pipe from this, and instead of cutting a door directly in the side of it, I decided to put a cutout on it. And then I used some of the additional extra to make extensions for these parts so that this sticks out a little further and this goes to the location I want it. Now this thing can be centered inside the mass exchanger. So I clipped out the extra metal, and now it sits, I think it's 4 inches there and there, and it's 1.5 inches along there. Initially, this video was supposed to be about the metalwork and the thermodynamics, the flow through the rocket mass heater. This is metal, but I'm gonna do it in the next video. Next video is supposed to be stonework and how heat moves around, but it's gonna have a little bit of metalwork too, because this is gonna explain a whole bunch of principles for me. Ooh, and I need to talk about shear angles in the next video. The next video is going to be super interesting. For me, it's fascinating because all of these simple scientific principles blend together and allow you to create really fantastic things. Not that a rocket mass heater is that fantastic, but fantastic for me because won't freeze out here anymore. If you're a patron, don't forget to check Patreon in the next couple days for that video that I'm releasing where I'm going to make fun of those hippies. Anyway, that's it for this one. I remember when hippies used to be out for the good of everybody and selfless and wanted to save the earth, and now they're just hypocritical liars. I feel like hippies used to be cool. I don't know where they went wrong.